So hello everyone, welcome back to my channel. Today we have questions again from NCERT. So question number 11 of NCERT, we have started this P block elements, and this class is daily from 8 p.m. to 8:45 p.m. right? So question number 11 is on your screen, that is, explain why ammonia is basic while BiH3 is only feebly basic, right? So ammonia is basic. Why is it so? Ammonia is basic because in ammonia nitrogen has one lone pair and three bond pairs. So due to the presence of lone pair, they are basic. Due to the presence of lone pair, they have ability to donate it, so they are basic. They are means if this nitrogen is replaced by element, this element is, what is this element? This is nitrogen, phosphorus, arsenic, antimony or bismuth, right? Now every element of group 15 when attached to hydrogen, its formula is EH3. It has 3 bond pairs and 1 lone pair. So why ammonia is more basic while BiH3 is feebly basic? This is the question. So answer is, as we go down the group, size of the atom increases. So as size of the atom increases, electron density decreases. So as electron density decreases, its ability to donate the electron obviously decreases because electron density decreases. So ability of element hydride to donate electron pair decreases as we go down the group, and that's why ammonia is more basic. Ammonia is basic while BiH3 is feebly basic. Means order of basic strength is, most basic is ammonia, then it is PH3, then ASH3, then SBH3, and least basic is BiH3. Why is it so? Because as we go along the series, or we can say as we go down the group, size of the atom increases, electron density on that particular element decreases, and so its electron donating power. And this is the order of basic strength. Got it? Okay. Question number 12. Question number 12 is nitrogen exists as a diatomic molecule and phosphorus as P4. Why? Yes, can you tell me? Yes, beta. Nitrogen exists as diatomic molecule and phosphorus as P4. So see, nitrogen, first thing is nitrogen is small in size. Nitrogen is small in size and has ability to form strong p-pi bond. Keep in mind what I said. Nitrogen is small in size and has ability to form p-pi bond. Okay, strong p-pi bond. That's why nitrogen exists as N2 because there is a triple bond between nitrogen and nitrogen. Okay, but phosphorus being large in size and at the same time pp single bond is stronger than nitrogen single bond. Surprisingly, it's true. Why is it so? Say phosphorus, it has lone pair. Nitrogen also have lone pair, but nitrogen being small in size, these lone pairs are close to each other. Therefore, there is large inter-electronic repulsion between the non-bonded pair of electrons. In this case, there is large inter-electronic repulsion between non-bonded pairs. Okay, that's why NN single bond is weaker. NN single bond is weaker than phosphorus single bond. So first thing, PP single bond is stronger than nitrogen single bond, and second, phosphorus being large in size cannot form strong p-pi bond. It has ability to form single bonds. It satisfies valency by forming pp single bonds. So it exists as P4. Phosphorus that form single bonds like this. Though this angle is 60 degree, there is large angle strain, P4 is unstable, but because nitrogen can form strong p-pi bond, that's why in between two nitrogen there is a triple bond. One sigma bond and other two pi bonds. But phosphorus cannot form structure like this because of its large size, and it has very weak pi bond, but it has stronger sigma bond than nitrogen that we have discussed. So because of strong pp single bond and means very less ability to form pi bond, pi bond, that's why phosphorus form P4 structure. Phosphorus has P4 molecules. Phosphorus is in the form of P4 molecules, right? Yes, beta. Only Manjot is there. Okay. Question number 13. Write main difference between properties of white phosphorus and red phosphorus. Now, first difference is in between structures. White phosphorus has structure like this. White phosphorus, structure of white phosphorus in which each phosphorus is sp3 hybridized. Each phosphorus is sp3 hybridized, but this bond angle is only 60 degree. So due to large angle strain, due to large angle strain, P4 is highly reactive. P4 is highly reactive. So first is difference between structures. So white phosphorus exists as discrete P4 molecules, but in red phosphorus, this is about white phosphorus. Okay, in red phosphorus, if you see its structure, in red phosphorus again there are P4 molecules, but these P4 molecules are joined together by single bonds. Okay, and therefore there is a chain of P4 units. Means red phosphorus is linear chain of P4 units, and white phosphorus has discrete molecules. And out of white phosphorus and red phosphorus, which one is more stable? Yes, beta. Can you tell me? Yes, Manjot. Out of white phosphorus and black phosphorus, black phosphorus is most stable. That is the third form of phosphorus. Okay, allotropes of phosphorus are white, red, and black. Yes, white phosphorus on exposure to light, it turns yellow. On exposure to light, it turns yellow. That's why it is also called yellow phosphorus. On exposure to light, जो white phosphorus है, it turns yellow. That's why it is also called yellow phosphorus. Okay. So first difference is in structure of white phosphorus that has discrete P4 molecules. There is a large angle strain, but in red phosphorus, these P4 units are joined together in a linear fashion. Okay, and that's why their this stress or angle strain is somewhat relieved, and that's why red phosphorus is more stable than white phosphorus. So this is the point of difference. First is in the structure, second is in the reactivity. That means white phosphorus is more reactive than red phosphorus. Now, next part, preparation. So, white phosphorus can be prepared from the phosphate rocks by reacting with sand or coke. Okay, see, in phosphate rocks there are calcium phosphate. So calcium phosphate when react with silica or phosphorus pentoxide means P4O10 when react with coke, So we get white phosphorus. Yes, what are the products formed? Tell me. Yes, beta. Manjot, are you understanding all this? I think Anika, Abhay, no one is there today. So you are the only one. Yes. So it react at very high temperature of the order of 773 Kelvin. So we get calcium silicate, along with white phosphorus. Or even P4O10 when react with carbon at very high temperature. Now tell me, temperature is very high. So carbon dioxide is formed or carbon monoxide is formed? Yes, beta. What is formed? Carbon monoxide or carbon dioxide when temperature is high? When carbon react with, means obviously phosphorus pentoxide is an oxidizing agent, okay, or carbon act as a reducing agent. So when oxygen combined with carbon, white phosphorus, preparation is of white phosphorus. So first is white phosphorus. Along with white phosphorus, tell me what is formed? Carbon monoxide or carbon dioxide? Beta, organic will start, um, see, after P block we have D and F, then coordination. So after 2 chapters. Very good, Prasad. Carbon monoxide, keep in mind, whenever carbon react with oxygen at very high temperature, there is a formation of carbon monoxide only. Carbon dioxide is not formed because carbon monoxide is more stable at high temperature, thermally more stable at high temperature than carbon dioxide. This is very important thing. Okay, just balance it. So 10 CO. Now calcium phosphate, so 3. So okay, 2. Okay, sorry. 4. So P4 and 3 to the 6. 6, right? So is it balanced? Is that white calcium silicate and white? Oh, that means in first case we get P4O10 because calcium phosphate first react with silica, sand at 1773 Kelvin. So we get P4O10. Then P4O10 is reduced by coke at the same temperature to get white phosphorus along with carbon monoxide. So this is the method of preparation of white phosphorus. Okay. Now, as I said, it is highly reactive. So when it comes in contact with air, action of air. So when white phosphorus come in contact with air, it burns spontaneously. It catches fire spontaneously to get P4O10. P4O10, and there is a glow, and that glow, that is called chemiluminescence or phosphorescence. That means white phosphorus glows in dark. White phosphorus glows in dark because when there is a air, air is there even in the dark. So P4 react with air O2 to give P4O10, and it glows with greenish flame. Okay, so it looks like greenish, and that is called chemiluminescence or phosphorescence. And at the same time, it is highly poisonous. It is highly poisonous. The people working or workers which are working with white phosphorus, they develop a disease called fuzzy jaw, where there is a decay of jaw. Because of that disease, there is a decay of jaw. Fuzzy, spelling of fuzzy, P-H-O-S-S-Y. Yes, right. So this is the case. Then very good reaction of it is when white phosphorus react with boiling sodium hydroxide in an inert atmosphere of carbon dioxide. Inert atmosphere of carbon dioxide, it leads to the preparation of phosphine along with sodium hypophosphite, NaH2PO2. Means we get phosphine. This is white phosphorus. White phosphorus, when react with boiling sodium hydroxide in an inert atmosphere of carbon dioxide, we get phosphine and sodium hypophosphite. Okay, now this reaction is actually a disproportionation reaction. It is an example of disproportionation reaction. How is it so? You know, in white phosphorus, oxidation number of phosphorus is 0. In pH3, what is the oxidation number of phosphorus? Tell me. What is the oxidation number of phosphorus in phosphine? Fast, fast, tell me fast. Yes, beta. In this reaction, what is the oxidation number of phosphorus in pH3 and in NaH2PO2? Yes. So it is 3, 3. It is balanced down. Yes, beta, fast. What is the oxidation number of phosphorus in pH3? Very good, Abhay. It is -3. And what is the oxidation number of phosphorus in sodium hypophosphite? In sodium hypophosphite. Fast, fast. No one is there. Say in NaH2PO2, phosphorus, take it as X, oxygen -2, hydrogen +1, sodium also +1. So total it is 3 plus X minus 4 equal to 0. That implies x minus 1 equal to 0. X is plus 1. That means from 0 to minus 3 and 0 to plus 1. So P4 is oxidized as well as reduced. That's why this is an example of disproportionation reaction. And yes, Parth, Prasad Parth, good evening, beta. Even white phosphorus catches fire spontaneously in chlorine. Surprisingly, white phosphorus, when comes in contact with chlorine, it catches fire, leads to the formation of PCl3 and PCl5. So it catches fire in chlorine even. Means there is no presence of oxygen. Chlorine is present and it will react. Okay. So and catches fire. Because white phosphorus, because of angle strain, because its normal angle should be 109 degree 28 minute, but its bond angle is only 60 degree. So due to angle strain, it is highly reactive. So just balance it. Okay, P4 plus 6 Cl2 to give 4 PCl3, P4 plus 10 Cl2 to give 4 PCl5. Okay, yes, so it is about white phosphorus, or we can say yellow phosphorus. White is called yellow phosphorus because it turns yellow on exposure to light. Even it can react with metals like sodium. When react with phosphorus, we get sodium phosphide. Even silver can react with white phosphorus to give silver phosphide. Calcium can react with white phosphorus to give calcium phosphide. See, sodium is plus 1, phosphorus is minus 3. Okay, so 4, 12, 4, 12, 2 and 6. Right? Now come to next part, that is red phosphorus. So red phosphorus, and physically it is a translucent waxy solid. It is okay, but red phosphorus, there is a linear chain of P4 units. That's why it is a crystalline solid. It is a, see, first difference, it is a translucent waxy solid. Next difference, black phosphorus, and in red phosphorus, that is a crystalline solid. Even this white phosphorus can be converted into red phosphorus by heating at 573 Kelvin in an inert atmosphere. In an inert atmosphere of CO2. So white phosphorus we can convert into red phosphorus. And what I said, it is hard crystalline solid. White phosphorus, it is insoluble in water. That's why it is stored under water. White phosphorus, because it catches fire spontaneously in air. That's why it is always kept under water. Okay, because it is insoluble in water and at the same time that save it from air. Otherwise, if it is placed in air, it catches fire. That is, we just, I told you that phosphorescence, chemiluminescence takes place. Okay. Yes. Next part. It is red phosphorus is non-poisonous, but white phosphorus is poisonous. Then if we talk in terms of solubility, it is also insoluble in water and soluble in organic solvents. Same is the case with white phosphorus, that is also insoluble in water and soluble in organic solvents like CS2. Okay. Uh, yes, being uh, because it form linear chain, therefore it is denser than the white phosphorus, and being polymeric in nature, it is less reactive than white phosphorus. Okay. It also react with chlorine just like white phosphorus. It form PCl3 and PCl5. So these are the basic differences. Now question number 14. Why does nitrogen show catenation properties less than phosphorus? So keep in mind, catenation is proportional to element hydrogen bond strength. Sorry, element bond strength. What is catenation? Self-linking property. Okay, so catenation is proportional to element bond strength. And you know, phosphorus single bond is stronger than nitrogen single bond. Why? Because nitrogen being small in size, there is large inter-electronic repulsion between the non-bonded electron pairs. Nitrogen being small in size, there is large inter-electronic repulsion between non-bonded electron pairs, and that's why PP single bond is stronger than NN single bond. That's why phosphorus show more catenation than nitrogen. Okay, that's why phosphorus exists as P4, nitrogen as N2. Very simple question. Next, give the disproportionation reaction of H3PO3. So beta H3PO3 disproportionate to give H3PO4 and PH3. This is knowledge based question. Just balance it. This is a disproportionation reaction. So balancing, to balance it, first of all we write 2 H3PO3 because one H3PO3 is oxidized and other is reduced. Okay, so this is a disproportionation reaction. So you know, in H3PO3 oxidation number of phosphorus is +3. In H3PO4 oxidation number of phosphorus is +5. In PH3 it is -3. So +3 to -3, decrease in oxidation number by 6, +3 to +5, increase in oxidation number by 2. So just multiply this by 3, so that increase in oxidation number is equal to decrease in oxidation number. So it is 3, 3. Okay, it is visible. So it becomes 3 plus 1, that is 4 H3PO3 to give 3 H3PO4 along with 1 PH3. So this is the disproportionation reaction of H3PO3. Question number 16. Can PCl5 act as an oxidizing as well as reducing agent? Justify your statement. Yes, beta. Which one, beta? Can you repeat? Which one do you want me to repeat? Pradhan? Okay. Can PCl5 act as an oxidizing as well as reducing agent? Justify. We have to justify. So see, in PCl5, what is the oxidation number of phosphorus? In PCl5, oxidation number of phosphorus is +5. So you know, phosphorus can show maximum oxidation number of +5. It cannot show more than that, which is maximum oxidation number of phosphorus. So it can never lose more electrons. It can never act as, yes beta, if it cannot lose, means it cannot be oxidized. It cannot be further oxidized. So it can never act as reducing agent. It can never act as a reducing agent, but it can act as oxidizing agent. It can act as an oxidizing agent. Okay. Yes beta, it can act as a oxidizing agent. PCl5, you know, it is a chlorinating agent. So PCl5 when react with any element, so it can form PCl3. So phosphorus here it is +5, so it becomes like with silver, so it form AgCl along with PCl3. Okay, so in this way silver is oxidized from 0 to +1 and phosphorus is reduced from +5 to +3. So PCl5 can act as an oxidizing agent, but it can never act as a reducing agent, because in PCl5 phosphorus has maximum oxidation number. Battery low, please wait. Okay, even SN can be converted into SnCl4 along with PCl3. Okay, mean 10 from 0 to +4. Okay, or even PCl5 when react with hydrogen gas, it will give PCl3 along with HCl. Okay, so just balance them. Uh, uh, okay, SnCl4 and 2PCl3. So here hydrogen is 0, and in this case hydrogen is +1. Done. Next, justify the placement of oxygen, sulfur, selenium, tellurium, and polonium in the same group of the periodic table in terms of electronic configuration, oxidation state, and hydride formation. Okay, so beta, first thing, electronic configuration. So if we compare electronic configuration of oxygen, sulfur, selenium, tellurium, and polonium. So first is helium, 2s2, 2p4. Sulfur is neon, 3s2, 3p4. Selenium, argon, 3d10, 4s2, 4p4. Tellurium, krypton, 4d10, 5s2, 5p4. And polonium, xenon, 4f14, 5d10, 6s2 and 6p4. Okay, oxygen is atomic number 8, then sulfur 16, selenium 34, tellurium, see here we add +8, then it is +18, again +18. Okay, so +18 means 52, right? Okay, then +32, so it becomes Z equal to 84. Okay, and electronic configuration is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. Okay, here it is helium, then neon, then argon, krypton, xenon, that is 2, 10, 18, 36, 54, right? So in this way, see, in all the cases, it is 3s2, 3p, means general electronic configuration of all the elements is general electronic configuration of these elements is ns2, np4. All of them are, they are p block elements, and group number is equal to 10 plus number of Ns plus Np electrons. So all of them belong to group 16. So first justification that they all are placed in the same group is that their electronic configuration, valence shell electronic configuration is same, therefore they are in the same group. Now second is oxidation state. Oxidation state. Now oxidation state, so you know oxidation state of oxygen is -2, being most electronegative, its oxidation state is -2, sometimes -1 like in peroxide, or in rare cases only with fluorine it can show +1 and +2 oxidation state. Now all of these elements can show -2 oxidation state because after gaining 2 electrons they acquire next noble gas configuration. But as we go down the group, sulfur being slightly electronegative, oxygen being most electronegative, means more electronegative, or we can say most electronegative among these elements. So sulfur being slightly electronegative, it can also show oxidation number of -2. It can also show oxidation number of -2. Rest of them can show positive oxidation state of +6, +4 and +2. +6, +4 and +2. So you can say according to oxidation number, to some extent they are eligible to occupy the same group, right? Last is hydride formation. So hydride, all of these elements, because after sharing 2 electrons with hydrogen they acquire noble gas config, they have complete octet of electron. That's why all of these elements exist as EH2, you know, H2O, H2S, H2SC, H2TE, H2PO. Means all of them can show -2 oxidation state, okay, but it is less probable as we go down the group. So here see, with hydrogen they form H2E type hydride. So all of them have same formula of hydrides. So as per hydride they should occupy same group. So in this way we justify that they can be placed in the same group. So that's all for the day. Thank you so much for watching this video. Do like, subscribe and share my channel. God bless you all. Happy learning. Jai Hind.